Hello and welcome to G Fun Facts Online. Imagine walking through a silent museum. You pass a case of ancient Roman silver coins. They look inert, just pieces of metal. But what if I told you they were whispering secrets? Not stories of emperors and battles, but tales of forgotten trade routes and bustling ancient economies. These secrets aren't written on the surface. They're locked deep inside the atoms of the coins themselves. Today, we're diving into the revolutionary field that lets us hear these whispers, digital archaeometry, and its most powerful tool, isotopic fingerprinting. This isn't your granddad's archaeology with dust and brushes. This is a high-tech journey into the past, revealing invisible connections between ancient civilizations. So what are these atomic secrets? They're called isotopic fingerprints. Think of it like this. Every material in the world has a unique chemical signature, kind of like a geological DNA. This signature is based on the ratios of its isotopes. Now, isotopes are just different versions of the same element. They have the same number of protons, but a different number of neutrons. These tiny variations in the mix of isotopes are the key to unlocking an artifact's origin. For example, the isotopic makeup of lead in a metal ore is unique to the specific mine it came from. By analyzing these fingerprints, scientists can trace an object, or even a person, back to its geographical source with incredible precision. How do they do it? The star of the digital archaeometrist's toolkit is an instrument called the mass spectrometer. This amazing machine separates isotopes based on their mass, allowing scientists to measure their amounts with extreme accuracy. And they can do it with incredibly small samples, which is great because you don't want to be drilling big holes in priceless Roman coins. There are a few key isotopes they look for. Lead isotopes are fantastic for tracing metals like silver and copper, helping us map out the metal trade in the ancient world. Strontium isotopes are absorbed from the soil and water into plants and animals. By analyzing strontium in human bones, we can tell if someone grew up where they were buried, or if they migrated from somewhere else. It's like a passport written in your skeleton. Then you have oxygen isotopes, which give clues about ancient climates and drinking water sources, and carbon and nitrogen isotopes, which can reveal ancient diets, and even point to trade in things like preserved fish. Okay, theory is great, but let's talk about some real-world detective stories. Take the Uluburun shipwreck, a Bronze Age vessel found off the coast of Turkey. It was a treasure trove, a time capsule of ancient trade. Isotopic analysis of the copper bars on board revealed they came from a completely different mine than anyone thought, totally redrawing the map of copper trade in the 14th century BCE. Or how about those Roman silver coins? By fingerprinting the lead isotopes in them, researchers have mapped out the vast scale of Roman mining. They can see how the sources of silver shifted over time, reflecting political changes and the opening of new trade routes. It's like watching the Roman economy ebb and flow by looking at the atoms in their money. The same techniques have been used to trace medieval alabaster sculptures back to their specific quarries in England and Spain, and to figure out that ancient Greece was importing luxury glass from both Egypt and Mesopotamia. So why call it digital times archaeometry? It's not just about the data analysis, it's a whole new way of working. Archaeologists now use high-resolution 3D scanning to create digital twins of artifacts. This means they can study them in minute detail without ever touching the fragile original. They also use Geographic Information Systems, or GIS, to map the isotopic data onto landscapes. This creates what they call isoscapes, basically isotopic maps of the world, making it much easier to pinpoint an artifact's home. And perhaps most importantly, they are creating huge, open-access databases. By sharing all this isotopic data, researchers can build more comprehensive reference maps, making future studies even more accurate. Now, it's not a magic bullet. Science rarely is. One of the biggest challenges is the overlap problem. Sometimes, different places can have very similar isotopic signatures. That's why researchers always combine this data with traditional archaeological evidence. There are also ethical considerations. Even taking a tiny sample means altering a unique piece of our shared cultural heritage. So collaboration with museums and respect for the cultures that created these objects is absolutely essential. But the future is incredibly exciting. As the technology gets even more precise and less destructive, and as our digital databases grow, we'll be able to answer questions about the past we never thought possible. We are learning to reconstruct ancient trade networks with a level of detail that was pure science fiction just a generation ago. So the next time you're in a museum looking at a pot, a coin, or a piece of jewelry, remember that it has a hidden story to tell. It's a story written in the language of atoms, a story of movement, of exchange, and of the intricate web of connections that shaped our world. The silent artifacts are speaking, and thanks to the incredible tools of digital archaeometry, we are finally learning how to listen. Thanks for tuning in to G Fun Facts Online. Join us next time for more amazing stories from the world of science.